Alrighty. Hello, my name is Leonardo Ledesma, and this is my AC to DC converter. Just a bit of background. The electric power conversion is a process of converting electrical energy from one form to another, such as AC to DC or DC to AC. The practice is used all over the world, for power delivery to houses and from an outlet to electrical device. For my application, I was given the constraints of 20 volts as my input voltage and 5k hertz for my frequency, and asked to output 20 volts DC. So this is the process that I'm going to be working with, and broken down into 4 steps. The first step is just to implement a step down transformer. The second step is rectifying that wave. The third step is smoothing that wave out, and then the fourth step is running it through a voltage regulator in order to get a true DC signal. The construction of this circuit implements a diode bridge design given to us in Lab 4, Circuit 4. The rest of the circuit was a simple assembly of basic transformer implementation and the usage of LT317A as a voltage regulator. The first step was to step down the voltage. So, in order to get from AC to DC, that involves using transformers here just to step down the voltage. I used a single phase input rated at 220 volts. I also had to add 0.1 ohms of parallel resistance needed in order for this to function to be allowed to happen in the simulation. I also had to find the turn ratio, which was given to us in voltage primary over voltage secondary, also equals turns primary over turns secondary, which is 220 over 20, or an 11-to-1 ratio. After finding that value, I was able to implement the structure into my circuit as shown here. With the turn ratio found, I made one side of the transformer have 110 microhenries and the other side just have 1 microhenry. This caused the voltage to drop to 20 volts, as seen here. We are given, this is showing our V-in of 220 volts at 5k hertz, and then this is our stepped down voltage reaching 20 volts, as shown here. Oh, and just to point this out, I also didn't fully rectify the wave as shown here. We were still giving a little bit of negative value. So, speaking of rectification, the second step, or stop for our voltage, is the diode bridge. That's arranged in a manner that only allows positive voltage to pass through due to the one-directional nature of the diodes. Due to my limited time, the design wasn't refined and the basic diodes were used. I feel like this issue right here can be solved by just getting more accurate diodes and like actually getting some that fit our case. So this is the step down was also the refraction. As you can see, we're only getting mainly positive values here. The next stop for our voltage is smoothing. Now that we have the top portion of the sine wave, we need to close off some of those valleys. In order to do so, we're going to place this capacitor here, rated at 120 microfarads, in order to give us the appearance of DC by raising some of those low points caused by the sine wave's nature. Once we implemented that, we ran our simulation, and we started to get this awkward design, which was, at first it was just really zoomed in, but we can see that some of these points are just really jaggedy. And then once we zoom out of that, we're able to see that this is a lot smoother compared to this. The final stop for our voltage is to be run through the voltage regulator. In order to get true DC, we need to implement a voltage regulator whose job is to generate a fixed output voltage of a preset magnitude that remains constant. I chose to leave the adjustment feature on this alone, because anytime I tried to raise it or to add any sort of resistance or anything to try to stimulate a change in our final voltage, it either caused a drop in voltage or no perceivable change. So just being run through, at first it seems like there's no difference in between V final and V and just our perceived DC out. But once we took a step back, there was a minor, like, more pure smoothing out of this. But we did lose some of our voltage. It dropped down to 19.26. That's important to note there. So some of our problems that we encountered, the first problem obviously was the voltage in parallel with the transformer. In order to fix that problem, we simply just added the internal resistance to the voltage source. I did try adding it in line here, right about here, but anytime I did, it either caused the simulation to just run into problems with my PC, or either it caused it to run the simulation really poorly. So I just decided to go with the easier route, which was internal resistance. Our second problem was that we improperly used the transformer formula. I was not placing the 110 microhenry on the correct side, which caused us to miss it in our troubleshooting phase, and it caused like multiple iterations of this circuit to be scrapped. So I pretty much was putting the 110 microhenries on the right side and the 1 microhenry on the left, because I thought I was doing a 1:11 ratio, but instead I needed, for every 11 turns here, we produce 1 turn over here. The issue was causing us to try to do a step up instead of stepping down, so that was causing further issues down over here, which was just creating like anomalies in the simulation that just really didn't mean anything at all. Let's go back. So then our final issue was with the voltage regulator. The voltage regulator was a new component for me, so I searched all over for references or anything, and it seemed like most people were just making their own versus the one provided to us. So I just stuck with the one provided by the software due to my time constraint. I was trying to add resistance or like stimulate it with any sort of like another DC source at the bottom of the adjustment function. However, that was just causing us to have undesired effects, so I simply unplugged the adjustment function and left it alone. The results. I was given 220 volts AC and 5 kHz and asked to turn it into 20 volts DC. I was able to implement a full wave refractor that incorporated a diode bridge and a capacitor to smoothen out the refracted wave and give a perceived DC signal. But due to my inability to use the voltage regulator, we were not able to get true DC. So here is our voltage in, 220 volts, 100 or 5 kHz, and then this was supposed to be our 20 volts DC. In conclusion, I feel like this was actually a great chance for me to experience a tight deadline with limited time and other constraints. That being said, my biggest critical mistake was not reaching out to others, such as my TA, for help sooner, or another experienced professional for aid. I feel as though my design is very close to being able to properly function with a few more adjustments, such as proper implementation of that voltage regulator and better transmission usage. AC to DC conversion is used all over the world and can be found in every household in abundance of consumer electronics. Being able to implement a design like this is a critical part for power supplies and larger applications. Here is some of our references, just the Microelectronics 8th edition and previous EE Lab instructions. Now for the demo portion, we are going to show here. This is our circuit, obviously sine wave 220 volts, 5 kHz, internal resistance 0.1 ohms. We gave it a bit of time for steady state, and here is our first stop, which is V in. As you can see here, we have at the bottom it says 220, just about. So next we're gonna do step down voltage. So now here we are given the 20 volts, and you can see the error here where it's not completely stepping or rectifying it all the way up. So we're still getting a little bit of negative, which is about negative 1 volt, just about, or 0.83 volts in the negative direction. So after that, we're supposed to be our next stop, which is the DC V out, or the perceived DC. So here we can see our jaggedy lines, and once we take a step back, we see that they're a little bit smoother than the previous one compared to this. Great improvement. Alrighty. Our next, oh geez, I'm sorry about that noise. Our next stop is after the voltage regulator. As you can see, like I mentioned, I left the adjustment feature disabled, and now our perceived volt DC 20 volts, as you can see, that should be about the same. It almost appears that we have a perfect DC signal, but it's 19.3 or 29 there. Thank you very much for your time. This was my 220 volts AC to 20 volts DC converter.